Assalamualaikum and good morning to the panel members and my supervisor, Madam Siti Nur Amalina binti Azlam. My name is Mohammad Hidayat bin Romram, and today I am going to present my final year project proposal entitled Cooling Load Analysis for the Proposed HVAC System at the Surau Al Hadid. Next, to give you an overview of today's presentation, I have structured my talk into 12 key sections. I will begin with the introduction and background of the study to establish the context of why this research matters. Then, I will address the problem statement, objective, and scope of work to define the boundaries of my project. After showcasing the expected result, I will deep dive into the research background, looking closely at the location, human thermal comfort parameters, and fundamental HVAC mechanics. I will then compare typical air conditioning system used in Malaysia. Finally, I will guide you through my methodology, including my preliminary calculation findings and the literature reference that support this project. Let's begin with the basic definition. HVAC stands for heating, ventilation, and air conditioning. Its core purpose is to regulate temperature, indoor humidity, air movement, and overall indoor air quality. Here in Malaysia, we experience a tropical climate characterized by high ambient temperature and high relative humidity levels throughout the entire year. Because of this heavy environmental load, building interior can become thermal trapped. Therefore, it is absolutely crucial for public and religious buildings to incorporate an optimized cooling system to maintain safe, comfortable, and productive indoor thermal conditions. Looking deeper into the background, religious places like mosques and surau in Malaysia present a highly unique operational pattern compared to typical office buildings. They experience intense, sudden peak usage during congregational prayer times, which create an immediate spike in internal heat and moisture production from the worshippers. Currently, the majority of religious buildings manage their indoor environment using a combination of split-unit air conditioner and mechanical fans, including wall-mounted and pedestal units. Academic literature suggests that the target indoor thermal environment for religious structure in Malaysia should ideally be controlled between 21.9 Celsius to 25.3 Celsius to achieve a balance between human comfort and energy conservation. A major issue right now is operational behavior. Air conditioners are often turned on right before the call to prayer and turned off 10 to 20 minutes immediately after prayers end. This causes indoor temperature and humidity level to rise rapidly right after shutdown, putting heavy thermal stress on the building structure and reducing operational efficiency. This brings us directly to the problems my project aims to address. First, during peak congregational prayer time, the rapid accumulation of people caused a dramatic increase in sensible and latent heat loads, creating a stuffy and uncomfortable environment for the congregation. Second, due to Malaysia's hot climate, there is an ever-increasing dependency on active mechanical cooling, which results in especially high electricity bills and operational costs. Third, and most importantly for an engineer, any error in the initial cooling load calculation can completely degrade the performance of the HVAC system. If the system is oversized, it leads to rapid short cycling, high energy waste, poor humidity control, and high upfront installation costs. If it is undersized, the system will run continuously without ever satisfying the room's comfort requirements, leading to high maintenance costs and occupants' discomfort. To solve these precise issues, I have established two clear measurable objectives for this study. First, to analyze the cooling load requirement of the campus mosques, thoroughly taking into account variables such as the building envelope material, occupancy number, electrical equipment, and required fresh air ventilation factor. Second, to determine the precise required cooling load capacity for the proposed HVAC system, measure in kilowatt or refrigeration tons, based on the calculated total peak heat gain of the Moscow structures. The scope of this project is strictly defined to ensure a focused and accurate engineering analysis. We focus specifically on the cooling load demands of Surau Al Hadid based on its unique environmental and architectural parameters. To achieve this, I will gather on-site dimensional data, identifying the construction materials used for the walls, floors, and roof, mapping out the layout design and tracking local weather profiles. The mathematical calculation will be conducted using the CLTD or cooling load temperature difference method, which is preferred by engineers for its reliable approximation of heat transfer through a building envelope. I must clarify the boundaries of the study. This project focuses entirely on the engineering analysis and capacity sizing of the air conditioning system. It does not cover the physical installation, dashboard layout design, or financial cost-benefit analysis. What do we expect to achieve by the end of this study? We expect to deliver a highly accurate estimation of the peak and average cooling load required for Surau Al Hadid. This analysis will break down exactly how much the heat is coming from solar radiation through the building envelope versus internal load like lighting, appliance, and metabolic heat from human breathing. We will determine the final required capacity in kilowatt or refrigeration tons needed to stabilize the surround within the recommended comfort range of 21 Celsius to 26 Celsius. By verifying the calculation through the CLTD methods, we will eliminate the guesswork, ensuring that the proposed HVAC system is neither oversized nor undersized, thereby maximizing energy efficiency while minimizing long-term operational costs. Let's take a closer look at the research location itself. The study is centered at Surau Al Hadid, situated within the University Technology Mara UiTM campus Bukit Besi. As a central campus facility, this building serves a high volume of students, academic staff, and campus visitors throughout the day. It is not only used for the 5 daily prayer, but also hosts religious seminar, community activity, and student academic gatherings. Because of its constant, combined with the high outdoor ambient temperature and heavy humidity specific to the Bukit Besi area, establishing an accurate data verified thermal profile for this building is essential to ensure occupant well-being. As engineers, our primary goal when designing an HVAC system is human comfort. Thermal comfort is governed by a delicate balance of dry bulb temperature, wet bulb temperature, relative humidity, and fresh air ventilation. In Malaysia, the generally accepted indoor comfort range falls between a dry bulb temperature is 23 Celsius to 26 Celsius and a relative humidity between 13% to 17%. When the relative humidity outdoors or indoors is extremely high, the air becomes saturated with moisture, which drastically increases the latent heat load inside the buildings. When this happens, the cooling coil in an air conditioner must work twice as hard, not just to lower the temperature, but to condense and strip moisture out of the air. This result is significantly longer cooling cycles, higher strain on the compressor, and an inflation of operational energy costs. Additionally, we must factor in ventilation. High concentration of carbon dioxide from packed crowd can make congregants feel drowsy
and stuffy. Even if the room temperature feels perfectly cool, thus introducing fresh outdoor air is mandatory. To understand how we counteract these thermal loads, let us examine the engineering mechanics of a standard HVAC system. A typical system operates on a vapor compression refrigeration cycle consisting of a compressor, a condenser, a metering device, and an evaporator. The system draws in warm temperature air from the room, mixes it with a fresh supply of outdoor air for ventilation, and forces it through an air filter. This filter is crucial because it traps dust, dirt, and particulates, protecting the internal component from falling and maintaining clean indoor air quality. The air then blown across the cool evaporator coil to lower its temperature and pulls out moisture before being distributed back into the zone by high-pressure supply fans. Advanced systems utilize sensors for temperature, humidity, and differential pressure before and after filter to dynamically adjust to changing occupant load. When looking at the standard market option in Malaysia, the two most widely implemented air conditioning systems are split unit system and ceiling cassette system. Wall-mounted split units consist of an indoor evaporator and an outdoor condenser unit connected via refrigerant piping. They feature a lower installation cost and are highly straightforward to clean and maintain, making them highly efficient for smaller, isolated spaces like bedrooms or standard office. However, they only blow air in a single direction, which can create localized cold and hotspot in large areas. Conversely, ceiling cassette units are integrated directly into the ceiling framework. They distribute conditioned air in multiple directions simultaneously, providing a much more uniform temperature gradient across a wide area. While ceiling cassette require a higher upfront investment and ceiling structural work, they are far more efficient for wide, open concept space such as community hall, open office, and surrounds when where consistent cooling for a larger crowd is required. Now, I would like to direct the panel's attention to my preliminary finding result, which demonstrate the initial step of my engineering calculation. I have begun calculating the within envelope solar heat gains using the official CLTD equation and data table. I physically measure the structural dimension of Surau Al-Hadid using a measuring tape to find the absolute area of the walls and the glass elements. The wall area was separated from the glass area because concrete and glass exhibit completely different heat transfer.
That's all from me. Thanks for watching.